Yeah, so first I would like to thank Adrian for the invitation and as introduction. So this is a joint work with Sasa Liao. She was my former PhD student, graduated last year. And Hao Zhu, yeah, he was a former visiting graduate student with me for 2 years. He's now a faculty at the Nanjing University. So yeah, let's look at this problem. Let me see. Oh, does not work. It looks like, oh, okay. Yeah, that's good. Yeah, so first let's look at the problem. So we want to look at the 2D Euler equation in a infinite cylinder. So the x direction is periodic. So let's put the periods to be 2 pi. And for the y direction is the whole axis from minus infinity to infinity. So we look at this Euler equation. Yeah, I think most of you, yeah, every of you should be quite familiar with this equation. So maybe I'll skip trivial details. So for this Euler equation, we can take a vorticity form. Right? Vorticity now is a scalar function. Is defined to be minus Laplacian of per c. Per c is the string function, and the u is determined. The velocity is determined by the string function in this way. Okay, now for the vorticity equation, it becomes a sort of transport equation, right? Okay, so okay, now let's look at the static solution we are looking at. It's called the Stewart's vortex solutions. So the solution is of this explicit form. This equation number 3. It gives you a string function. The string function is given by this explicit formula. Okay, so you can see in this formula there's a parameter epsilon. So epsilon can take any value from 0 to 1, including epsilon equals 0. But of course, you cannot put epsilon equal to 1. This would be meaningless, right? But we're going to see when epsilon tends to 1, it actually has a very important physical meaning. Okay, now let's draw the string lines associated with this steady state. So for this, for the flows with this string function, you can draw the level curves of this function per c epsilon. So it looks like this form. So if you just take one period, so this is 2 period from minus 2 pi to 0, 0 to 2 pi. So if we just look at one period, actually these 2 points are the same, right? So yeah, if you put the two periods together, it looks like 2 eyes of a cat, right? So that's why this flow is also called a cat's eye flows. Okay, and then you can see in the middle, these 2 points corresponds to the like a minimum point of the function psi epsilon. Yeah, we can see they are the elliptical critical point, and for these 3 points, they are the hyperbolic critical points. They are all the stagnation points. In other words, the velocity is equal to 0 at those points, right? But this is a hyperbolic critical point. So in particular, the Lyapunov exponent is positive here, right? And these 2 points are the elliptical critical points. The Lyapunov exponent is 0 there. Right? Okay, so so this is the pattern of the string lines. So this is called Stewart's vortex solutions because this was first wrote down by Stewart in the 1967. But actually, we're going to see this. This solution actually was discovered by plasma physicist even before Stuart. We're going to see some history. Okay, now let's look at vorticity. So the vorticity is the minus Laplacian of the string function. It takes this form, and for the velocity, it takes this explicit form. In particular, you can see when y go to infinity, velocity will tend to 1, 0 at the plus infinity, and it will tend to minus 1, 0 at the minus infinity. So, and if you look at the equation satisfied by the string function, you see it satisfies this Liouville equation, right? Liouville equation number 4. Okay, so let's look at the two ends when epsilon tend to 0 and the epsilon tend to 1. If you put the epsilon equal 0, you'll get a shear flow. It has this kind of a tangent HY profile. It's called a mixing layer shear flow. When you let epsilon tend to 1, of course, we cannot put the epsilon equal to 1 directly, but you can send the epsilon tend to 1. Then this will give you a point vortex system in the limit. In other words, the vorticity will be a delta function concentrated at the lowest points. Okay, so you'll get a point vortex system consisting of a bunch of point vortices, point vortex. Okay, so this is the singular limit. And so why should we study this kind of flows? Because it has a lot of applications. For example, it's a typical phenomenon in the ocean, and also in industry, used as a efficient mixing strategy, and also it's also used to describe a tropical storm. It has a bunch of applications. Now let's look at some brief history of this kind of flows. Kelvin first studied this kind of flow of this cat's eye pattern, but he didn't write down this kind of exact solution formula. And Lamb, in his famous textbook on fluids, look at a point vortex system. In other words, the limit epsilon tend to 1. And then Stuart, of course, wrote down this solution in 1960s. But even before Stuart, the guys I listed here, some reference actually like 1965, this before Stuart's. They actually discovered the same solution in other settings, like in plasma physics, actual physics, and also even to describe Saturn's rings in this 96 paper. So it has a bunch of other applications in different physical contexts. Okay, now let's look at the stability of these solutions. Yeah, this is a steady solution. Of course, we want to know whether or not they are stable or unstable. So first, we should mention, maybe just right after Stuart write down this solution, Carey studied the linear stability for double periodic perturbations. When epsilon is very small, he find the instability. Then in the 1980s, Pierre Humbert and Widner used numerical to study linear stability, but they need to do a truncation of the domain because the y direction is from minus infinity to infinity. They truncate the y direction to be finite interval from minus d to d. Then at the artificial boundary condition, vorticity is 0 on the boundary. But they can do some numerical to find linear instability for both 2D and 3D perturbations. And there's also some attempts to justify the nonlinear instability, nonlinear stability by Holm, Marsden, Latour in 1986. But they also need to do the truncation of the domain. So they basically truncate the fluid domain to be a finite domain bounded by two string lines. Maybe I can draw a picture here. Yeah, so they didn't look at the original cat's eye. They they do a truncation, like you truncate the domain to be bounded by these two string lines. So it becomes a finite domain. Then they look at this case I in this finite domain. They can find some sufficient conditions for stability. The reason they want to they need to do the truncation is only in this finite domain they have the Poincare inequality. This is very crucial when you do this kind of it's basically like an Arnold's argument to use this some Lyapunov functional to prove the nonlinear instability. But if you are in the infinite domain, you don't have this Poincare inequality. They cannot to get anything. But even if you do the truncation of the domain, of course, if you truncate the domain to be smaller, it's easier to get the stability. But even if you do the truncation and you still want to contain the case I, right? Then you do the truncation barely containing this case I. Even in this case, for this domain, just containing the case I, they also need to restrict the epsilon to be less than 0.527. Yeah, it's some kind of sufficient condition they need to impose. So in other words, the stability problem is still open for the original domain or for the domain with a sufficient large size. Okay, now let's look at a related problem in MHD theory. The MHD theory, so this is the MHD theory written in this string function and not a string function, electrical static potential phi and vorticity omega. So so this is the 2D MHD written in this formulation, and people find out actually even before Stuart, people find out this static solution. Yeah, just in the 1960s, a little before Stuart. Now the function. So now now this function numbers given by formula number 3 is not for the string function. It's for the electrical. It's for the magnetic potential. So the static solution in this setting is with no flow. The velocity is equal to 0, but you do have a magnetic field given by this Stuart function. The potential is given by the Stuart function. So it's called magnetic islands in this kind of setting. Okay, so and in this setting, a very interesting phenomenon is called coalescence instability. In other words, if you still look at this this picture, but now think of this is the magnetic islands. So if you have 2 islands, so they can give they have the instability. They actually, if you follow the nonlinear evolution, these 2 islands will start to merge. Yeah, we will form a larger island. Eventually, looks like a stable. But if you have 2 islands, it's called you have the coalescence instability. In other words, yeah, these 2 things will start to merge. Yeah. Any questions? The velocity is equal to 0. The magnetic potential is given by this function. So you have the magnetic field is like the velocity. The magnetic field is not 0, but velocity is identically equal to 0. So this is called the magnetic islands. So people are very interested in this kind of coalescence instability because it has an important implication for so-called magnetic reconnection theory. So yeah, in the 70s, yeah, these people find numerically you do have this kind of coalescence instability. Yeah, and yeah, we'll see later on. We actually gave a rigorous proof of this kind of coalescence instability, and also people also like the group of Hong and Marston and some other people, they also use this Arnold type of argument to try to prove nonlinear stability or even linear stability for this kind of magnetic island solutions. But they also need to do the truncation of the domain, and they can only get some sufficient condition for stability. Yeah, like a restriction of the parameter epsilon, or restriction of the size of the truncated domain, so on and so forth. Okay, now let me describe the results we obtained. Yeah, this is a very sort of very technical work. Yeah, we just posted a paper. Yes, about 120 pages. Yeah, it has a lot of details, but I just want to give you some main ideas of the results and the work. So first, let's look at a linearized system. So for the linearized Euler equation, we can write it in a Hamiltonian form, linear Hamiltonian form. So for a Hamiltonian form, we have this anti-symmetrical operator, symplectic operator J epsilon is a transport operator. So here it has this coefficient G prime per C epsilon. Per C epsilon is the studied string function, and the G is this exponential function. I think we defined it earlier here. Yeah, G is this exponential function. Okay, so this is the symplectic operator, and the self-joined part, the symmetrical part L epsilon is given by 1 over G prime minus the Laplacian inverse. And our space X epsilon is the following one. It's the weighted L2 space for vorticity, and the weight is 1 over G prime. But we also add a side condition. The integral of vorticity is equal to 0. So this is a very reasonable, actually is physical, because if you look at the integral of the vorticity is equal to 2 pi times the difference of the limit of the velocity at infinity. Okay, so remember for our steady flow, the steady velocity tend to non-zero limits at infinity, right? Tend to plus or minus 1, 0 at infinity. So when you do the perturbation, we want to keep this asymptotic limit, right? So in other words, for the perturbation of the velocity, it's going to vanish at infinity. So now if you look at the integral of the vorticity, it should be equal to 0, because the integral of the vorticity is 2 pi times the difference of the limits, difference of the horizontal velocity at infinity. So that's why when you look at the linear perturbations, this condition has to be there, and it is very crucial to have this restriction. Okay, now let's look at a corresponding space for the string function. For the string function, of course, we first we need to have a, let's say, in H1 dot. So this means the perturbation of the velocity is integrable. Is a square integrable, right? You have the perturbation of the velocity. Yeah, at least give you finite energy. So for the steady state, it has infinite energy, but we want to have the perturbation to have the finite energy. Okay, and we know for the 2D case H1 dot. Yeah, for this cylinder case, for H1 dot is not a Hilbert space, so we need a we add a condition 0 to 2 pi per c x0 dx is equal to 0. And for this space, a nice thing is if you add a weight G prime per c 0, per c 0 is one of the steady state of the Stewart solution. Then you do get a Poincare type inequality with this exponential weight. This decays exponentially fast at infinity. So we get this kind of Poincare inequality. Okay, now so for the Hamiltonian system, let me mention a general result obtained by myself and my colleague Chungchung Zhang a few years ago. Yeah, this is actually not the 2022, it's like 2017. So the formula we obtained for this very general Hamiltonian system is, so for one conclusion is the following. So for the right-hand side is the number of negative directions of the quadratic form of L ipsum. So if you write down the quadratic form of L ipsum, you can count how many negative directions it has. So let's denote it by m minus L ipsum. Okay, now the left-hand side give you a bunch of numbers associated to the eigenvalues of this operator J ipsum, L ipsum, JL. Okay, so remember the spectrum of JL is what we want to find out, right? Okay, so let's four numbers on the left-hand side. So one is KR counts the number of eigenvalues on a positive axis. So here we only look at the eigenvalues on the first quadrant, because for this Hamiltonian system, the spectrum is symmetric to both real and imaginary axis. Okay, so KR counts the number, the total number of eigenvalues, including the algebraic multiplicities on the positive real axis. And for KC, it counts the complex eigenvalues. And for Ki less or equal to 0, it counts the imaginary eigenvalues. But we only count the non-positive dimensions restricted to purely imaginary eigenvalues. So it's also called a negative Klein signature. And for K0 less or equal to 0, we count the number of non-positive directions restricted to the generalized kernel space. Okay, so these four numbers add up to the number of negative eigenvalues of L ipsum. Okay, so if the first two numbers, if one of the first two numbers is not 0, we get the instability, right? Okay, so in particular, if the right-hand side is equal to 0, we get a spectral stability, right? Okay, now let's count this number m minus L ipsum first. So let's see what's this number. So this is reduced to solving a spectrum problem. So remember, L ipsum is this operator for vorticity on this space. So it is more convenient to study a related operator for a string function. So we can equivalent solve a eigenvalue problem for this string function operator. So it's minus Laplacian minus G prime times identity minus a projection. It's a 1D projection operator. Okay, so if you know the number of negative directions of this operator, then it gives you this number. It's the same. Okay, so this is a reduction, but it's easier to do the commutations for this operator because it looks like a familiar elliptic type operator. Okay, so so for this eigenvalue problem, so let me keep the things short. Just give you the result. So first, for the case ipsum equals 0, we can use separation of variables. We can actually find all the explicit eigenvalues. So here we are solving this eigenvalue problem, 15. So lambda is our eigenvalue. So lambda equal to 1, you can see it corresponds to the 0 direction for the quadratic form. Okay. If lambda equal greater than 1, this corresponds to the positive directions. Lambda less than 1 corresponds to negative directions for the quadratic form. Okay. So for this spectrum problem number 15, we are able to find all the explicit eigenvalue and the eigenfunctions. So in particular, there's no negative directions. The negative dimension is equal to 0, and then there's a 3-dimensional kernel space. Okay, so this is for the case ipsum equal to 0. you can use separation variables. It's reduced to a bunch of ODE spectrum problems. Okay, now how about the case when epsilon is not equal to 0? Then this is a PDE operator, right? It's a PDE operator. So yeah, at the beginning, we think it might be hopeless to find an explicit formula for this PDE operator. It's much harder than an ODE case. But actually, first we try to get something for epsilon small. We think we might be able to get it from perturbation from the ODE results. Then we also do some numericals. Then to our surprise, the spectrums of this PDE operator looks very much like the ODE case, at least for the first three eigenvalues, is 1, 3, and 6. They look identically the same as the epsilon equal 0 case. And also, when we play with the eigenfunctions, we see there's a certain pattern. Then, and we use numerical to double check these things. Then this gives us confidence. Maybe for the PDE case, the spectrum can be reduced to the epsilon equal 0 case. And actually, after some effort, we are able to find a transformation. So here, yeah, the transformation is given explicit here. Yeah, maybe I will skip these details. Yeah. So anyway, we are able to use a transformation to reduce the spectrum problem for epsilon not equal 0 to the case epsilon equal 0. And we find, yeah. 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 At the beginning, we don't believe this thing. Yeah, but at least numerical shows is the case. Then we also find at least the first few eigenvalues. We can play with it. We find indeed it's given by 1, 3, and 6 is the same as the first 3 of the epsilon equal 0 case. Then we are able to find a transformation. Actually, will reduce the case epsilon does not equal 0 to epsilon equal 0. Yeah. Yeah. It covers the whole range of epsilon from 0 to 1. Yeah. So we are able to find. Yeah. Yeah. You mean some intuition why this is true? Yeah. So we didn't look very deeply into the reason. Yeah, the transformation is given explicitly here. Yeah, it's not easy to see why this works. Yeah, after some trying. Yeah, but yeah, numerical here definitely play an important role. Yeah, we see some patterns by doing numerical and also by by finding the first few eigenvalue and the eigenfunctions. Yeah. Yeah, this gives you some hint of why this transformation will work. But at the end, we are able to find all the eigenvalues and the eigenfunctions of this PDE operator. Yeah, we find out the eigenvalues are the same as the case epsilon equals 0. So in particular, it tells you for the quadratic form, it has no negative direction and it has three-dimensional kernel space. And the three-dimensional kernel are given by the derivative of the static solution to the derivative x, y, and the epsilon. For the first two is not surprising because the problem is a translation imbalance in both x and y direction. So you expect that you should have two translation modes. But the third one is not obvious. The derivative to the parameter epsilon is also in the kernel. Okay, and this also play a very important role when we do the nonlinear stability. Okay. Now if you know there's no zero direction for the quadratic form, of course, by using this Hamiltonian formulation, we know immediately it's spectrally stable for the perturbations of the same period. So this is the perturbation for the same period, for the 2 pi period. Okay, yeah. This is Yeah. So here we take one case I, just one for the period is 2 pi. Yeah, because only this case is stable. Yeah. Uh-huh. Uh-huh. Oh, then yeah, because for this Stewart solution, it's not periodic in Y. Yeah, it's not, because you see, yeah, it tend to 1, 0 at the plus infinity, it tend to minus 1, 0 at the infinity, right? It's definitely not a periodic in Y. Okay, so this is the case for 2 pi period. We call it co-periodic perturbations. Okay, now let's look at the perturbations of double period or triple period, right? So in other words, you look at more than 2 eyes, right? If you only look at 1 eye, it looks like it's stable for any epsilon between 0 and 1. Okay, now how about the case when we look at 2 cast eyes or 3 cast eyes? So we can prove it's always unstable. If you have more than 2 eyes, two or more is always unstable. Okay, so how do we prove this instability? To prove this instability, again, we use the Hamiltonian formulation. But if you go back to our original Hamiltonian formulation, you have this nice formula. But if you try to play with this formula for the case with double or triple period, the right-hand side, you can still compute the spectrum. Yeah, you can also compute it explicitly. It's not 0. Okay, so for 2 pi case, I think this is equal to 2. So it's definitely the right-hand side is not 0, but it does not help you here, because you see, yeah, if right-hand side is equal to 2, now you cannot say which one. So you want to conclude either Kr or Kc is not equal to 0. This gives you instability. But if right-hand side is equal to 2, it could happen Kr is equal to 0, Kc is equal to 0. But Ki less equal to 0 is not 0, right? So, but if you have imaginary eigenvalue, this is neutrally stable, right? Okay, so yeah, it's very difficult to exclude this imaginary eigenvalues if you play with this kind of index formula. If the right-hand side is happen to be an even number, right? But of course, if it's odd number, then you can immediately see at least Ki is not equal to 0, right? Okay, yeah, and usually this K0 less equal to 0 can be find out explicitly. Okay, so it's difficult to play with this kind of index formula. So, but for this problem, we are able to find another Hamiltonian formulation. It's called a separable Hamiltonian formulation. So this will do the work. So what's the separable Hamiltonian formulation? So it's sort of a, you can think of it as a more special Hamiltonian formulation. So here we do a even order decomposition for our perturbation, even order to x variable. So because for the steady flow is symmetrical to the middle axis to x equal to pi. So we do a parity decomposition with respect to this symmetric axis x equal to pi. Then we have even and odd space. So this will break our and we break our perturbation into even and odd part. Then we can write it as a Hamiltonian form of this shape. Okay, so you can see now the anti-self-joint part is off diagonal, and for the self-joint part, symmetrical part is diagonal. So we call this a separable Hamiltonian system. So for this kind of separable Hamiltonian system, in an earlier work with my colleague Zhang, we developed this sort of abstract thing for when we look at the stability theory for non-rotating stars of Euler boson system. So this is an abstract setting. So we have this separable Hamiltonian form. So we assume a few things. So first, the L only have the quadratic form for L only have a finite many negative directions, and the A you can think of A is positive to be simple. Yeah, A is positive. Then B can be quite an arbitrary densely closed operator. B prime is the joint of B. Okay. Okay. So under these conditions, So the main assumption is error, the quadratic form error only have finitely many negative directions. Then we can conclude the number of unstable modes of this linear Hamiltonian system, number 16. It has exactly this number of unstable modes. You want to count the number of quadratic form of L restricted to the closure of the range space of B. Okay, so this is the thing we want to compute. Okay, now if you apply this to this special case, now B and the L are given explicitly here. It basically is the same as before, but now you restrict it to even and odd spaces. Okay, now you get a criterion. So we want to, so the computing of the number of negative directions of L restricted to the range space of B is equivalent to find the negative direction of this Schrodinger type operator, elliptic type operator. Now it takes the form minus Laplacian minus G prime times identity minus another projection operator. So this is not a previous 1D projection operator. Now this projection is to the kernel of the transport operator B epsilon. So it basically is the phase space average of a function on a steady trajectory. So you can see this projection of a function is a constant on any trajectory of the static field. Okay, and the value on this is, trajectory is simply the phase average of the function phi. Okay, so this is the projection to the kernel of the transport operator. Okay, so this is a more complicated projection. So there's no, possibly no hope we can solve this spectrum problem explicitly like before. But here, in order to prove instability, we only need to find a text function such that this quadratic form is negative, right? So we don't need to solve the whole spectrum problem. As long as you can find one text function such that this quadratic form is negative, we're done, right? So the construction of this text function is in the following way. So for the double periodic, even multiple of periods, the construction is like this. In particular, the non-local term becomes 0 when you choose this kind of text function. So you can compute this quadratic form explicitly is indeed negative. The construction for all the multiple, like a triple period, is much more subtle. So we're not describing here, but we can still get it done. So this proof for any multiple period is always unstable. Okay, so this is the instability for multiple periods, and we can actually did this thing even for so-called modulational instability. Yeah, this is like a Benjamin fire instability for water waste, for Stokes waste. So we look at the perturbations of this form. It's a 2-pi periodic function times a factor E I alpha x. Alpha is the modulational parameter. So here we can take alpha to be between 0 and a half, because for alpha to be general number, it can all be reduced to this range. Okay, so we look at a modulational parameter alpha. If alpha equals 0, then we know it's stable. It's the co-periodic perturbations. So as long as alpha is not equal to 0, then we can actually prove it's always modulationally unstable. Okay, so this is another conclusion. Okay, now let me say a few words about the nonlinear stability for the Euler case. To prove the nonlinear, it's nonlinear orbital stability, because this problem has a translation invariance in x and y direction. So we are proving the orbital stability. So here we use a Lyapunov functional. So the Lyapunov functional has 2 terms. One is this the integral of vorticity. So here we break the vorticity into the steady part, omega epsilon, and the perturbation is omega. Now, so this is the first part of the invariant. The second part is called a pseudo energy, because we cannot use the traditional energy here. It's going to be infinite, right? Because the velocity tend to 1, 0, plus or minus 1, 0 at the infinity is non-zero. So if you do the integration of the velocity square, it is infinite, right? But we can define a pseudo energy. The pseudo energy is of the following form. So, so here first we write down a green function. The green function, maybe we didn't write it here, but the green function actually, I think it's of the, yeah, it's quite similar to actually quite similar to the Stewart function. Yeah, we didn't write it here. It's the convolution of vorticity perturbation and the vorticity, perturbable vorticity and the string of this green function. Then multiplied by vorticity, then you do the integral. So this thing gonna be finite, okay. So this is the pseudo energy. So our energy Casimir function has these two terms. Then of course, you try to do the, basically we try to do the Taylor expansion of this energy Casimir function around the steady state to show the first order variation is equal to 0. Then the second order variation is positive, right? Then the remainder term is a higher order, right? So, but if you try to do it this way, there's two difficulties. First is if you try to do the expansion in terms of vorticity, that's a trouble, because for the quadratic form, you can see more or less it's like the vorticity square. The L2 norm of this vorticity, more or less, right, is like this type of norm. So there's no way you can use this L2 norm of vorticity to control the integral of vorticity Q, right? Or integral of vorticity to power 4, right? So there's no way we can control this thing because there's no enough regularity. So here we need to do a sort of, we need to do a dual functional. So we need to transform this the function of vorticity to a function of string function. So we use a Legendre transformation. We can actually reduce this to a Taylor expansion for a related function for the string function, because string function has a higher regularity, at least is in H1 dot. So we can hope to get a better regularity of the reduced function. Actually, we can prove the reduced function is indeed a C2. Then you can do the Taylor expansion there. So this is the first trick we need to play. Then the second trick, of course, is now if you look at the second order variation, the second order variation of the reduced function is actually quite close to the operator we studied at the beginning. Is actually quite close to this operator. Okay, so we know this thing has a 3-dimensional kernel, right? So how do we get rid of these 3 kernels? 2 of the kernels you can get rid of it by using the translations x in y, in x and y. To get rid of the third kernel comes from the derivative to epsilon parameter. So first we enlarge the orbit from the 2D orbit to the 3D orbit. In other words, we put both x, y, and the epsilon to be the changeable parameter. So it becomes a 3-dimensional orbit. So first we prove the orbital stability for this 3-dimensional kernel. So this will take care of all the 3 kernels. It gives you the positivity of the second order variation of this reduced functional. Then in order to go back to the traditional orbital stability for 2D orbit to x and y translation, so we need to use an additional invariant to take to control the variation in epsilon parameter. We want to show the epsilon actually does not change much. Okay, so this will allow you to go back to the original 2D, the traditional 2D orbital stability result. So this is the these are a few details for the nonlinear stability. Okay. So and for the MHD, maybe let me just say one word here. We can do the same thing here. First, for co-periodic perturbations, for one magnetic island is stable, both linear and non-linearly stable. And for double period, we can indeed prove coalescence instability for any epsilon between 0 and 1. Okay, so this sort of justify the discovery of those physicists by numerical. So yeah, but yeah, for the it's a little more subtle. If you want to study the instability of like 3 islands, 3 magnetic islands, it's actually not yet done. Yeah, but for double periodic, we can also do it for MHD case. Yeah, for the triple period, it's also a lot more subtle for the OLA case. But for the MHD case, we are not able to, currently we are still working on that, But at least we can get the coalescence instability. In other words, if you have 2 islands, they are indeed unstable, Okay, so this is all I want to talk about here. Thank you for the attention.